So in this video we want to look at the geometric properties of cross products, whereas in the previous we talked about the algebraic properties. So we're going to let u and v be two non-zero vectors in three-dimensional space, and we're going to let theta be the angle formed by those two vectors. So the first claim is that when we take a cross product u cross v, the result of the cross product, the vector that we get, is perpendicular to both u and v. So we're creating a perpendicular or orthogonal vector. That's claim number one. Claim number two is that the size of the cross product, my pen is really messing up today. Claim number two is that the size of the cross product can be found by taking the size of the vector u times the size or length of the vector v, and then multiplying by the sine of the angle between the two vectors. Claim three is that if we take u cross v, we can find u cross v by taking the size of u sine theta, and then multiplying it by w hat, where w hat is just a unit vector perpendicular to both u and v. So this property 3 really comes from applying properties 1 and 2 simultaneously. We know that u cross v generates an orthogonal or perpendicular vector. So if we know the size of the vector, we can then multiply the size of the vector by a unit or length 1 perpendicular vector to get the cross product. We would need to be a little careful with direction. When we get two vectors, we either get a perpendicular vector pointing down or a perpendicular vector pointing up, depending on the direction we take the cross product in. So we'd have to choose the correct direction. And then claim number 4 is that the size of the cross product is the area of the parallelogram formed by the two vectors. So the proofs of these are, some of them are easy, some are hard. The proofs of properties 1 and 2 are a little bit more difficult. Just in the sense that the algebra you have to do leaves a lot of room for silly mistakes. And I know this because I've proven both of them using algebra, and I've made those silly mistakes. So let's talk through the proof of property 2. And so we do this just like we did trig identities. We pick one of the two sides. I'll pick this side. You pick one of the two, and you show it can be manipulated via a series of algebraic moves and identities into the other side. So if we start with size of u, size of v, sine theta, we can rewrite it as size of u, size of v times the square root of 1 minus the cosine squared. And the justification for this is we're going to make the claim that the square root of the sine squared of theta is equal to the sine of theta. And on its face it might seem like this is something that's okay to claim, but in general this would be wrong. In general, if you take the square root of something that's squared, you get the absolute value of that. So in other words, if x can be a negative number, when we square it, it becomes positive. So the square root of a positive number is going to be positive, so we need to take the absolute value of x. And because the sign can be negative sometimes, you have to justify that you don't need the absolute value sign. And the justification is that when we think about the graph of the sine function going from 0 to 2 pi, right here is pi radians or 180 degrees. And the idea is that when you have two vectors and you place them toe to toe, initial point to initial point, the angle that you get, theta, is going to run from 0 to 180 degrees. And from 0 to 180 degrees, the sine function is positive. So over the range of angles that you can get, the sine is always positive, or not positive, but non-negative, because sine of 0 and sine of 180 both equal 0. So it's non-negative, which is what we need. So because the sine is non-negative from the angle range from 0 to 180, we don't need the absolute value. And then once you're okay with writing this, then you use the Pythagorean identity. You recognize that cosine squared plus sine squared is 1, and this allows you to rewrite the sine squared as 1 minus the cosine squared. So that's where this step comes from. And then the jump to the next step is based on a previous result. We showed in a previous video that the cosine of theta has to equal the dot product of u and v divided by the size of u times the size of v. So if I have a cosine squared sitting in here, if I square both sides, I'm going to get exactly what I see sitting here. So we're just substituting based on a previous result. And then the next step, the move from here to here, is just take the stuff under the radical sign and find a common denominator. In other words, rewrite 1 as size of u size of v squared over size of u size of v squared, which gives you size of u size of v squared minus u dot v squared in the numerator. And it gives you a denominator down here that's going to have the size of u size of v squared. And then when we take the square root of that, we just get the size of u size of v, and that divides into size of u size of v and gives you a 1. So it cleans up like this. And then once you get here, it's just a matter of doing the operations. Take the dot product of u and v. There it is. And remember from a previous result, we have demonstrated that the size of u is just the square root of the sum of the squares of the vector components. So u sub 2 squared, u sub 3 squared. So if we're squaring it like we are here, that's going to, if we're squaring both sides, that's going to get rid of that radical sign. So we wind up with size of u squared being the sum of the squares of the vector components. The size of v squared is just the sum of the squares of the vector components. And then between here and here, there's a dot, dot, dot. So what you do is you multiply this all out, you multiply this all out, and you get 3 times 3 is 9 terms. And here you're squaring a trinomial type thing, so you're going to get 3 times 3 is 9 terms. So you wind up with 18 terms. And you have to reorganize them into a particular form. And they can be reorganized, and you usually make a lot of mistakes between here and here. I know because I have. You subscript something wrong, you make a u that looks like a v, and it messes up the calculation. So it's just a tedious calculation, but the idea is you can manipulate these into 1, here's 2, so that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 terms. So the 18 terms you get manipulate into 12, which means 6 of them cancel out because of pluses and minuses that are going on. And what you're doing is getting it in an a squared minus 2ab plus b squared form, which then factors as a minus b squared. So you're getting it into, you can see that form showing up in each spot. Each of these has been manipulated from here into that a squared minus 2ab plus b squared form, which allows you then to factor it in the a minus b squared format. So every step is pretty straightforward, except there's messy algebra between this step and this that I always, when I do it, I always make mistakes. Then that's life. So once you get it into here, what you want to recognize is that these guys in here are actually the components of the vector you get when you take the cross product. So here I have the sum of the squares of the components you get when you do u cross v. And if we have the square root of the sum of the squares, we know that that's the length or size of the vector, and that's the justification. So this one is painful to prove. It's painful. But once you get this one, for example, things like property 5 become easy to prove. So property 5 says that the size of the cross product, which you can see sitting right here, gives the area of the parallelogram that has u and v as adjacent sides. So this one now becomes simple to prove. You say, hey, I'm going to take my vector u and my vector v, and I'm going to put them initial point to initial point, and they're going to form a parallelogram. And I could dash that parallelogram down. And we know that the area of a parallelogram is going to be the base, the size of the base times the height of the parallelogram. So if we know the angle between u and v, and we drop a perpendicular down from u to v, we know that this right here is the height of the parallelogram. So if I know the size of u and the size of v, then from trigonometry, this height is just the size of u times the sine of theta, and that comes directly from trigonometry. So voila, you have it. The area of this parallelogram is going to be the length of the base, which is size of v, times the height, which is size of u. So you wind up with size of u, size of v, times the sine of theta, because the order we multiply these in doesn't matter. And once we're convinced that we can find the area of the parallelogram like this, if you've already done the hard work to show that this is the same as this, then that demonstrates the claim for you. Hey, I can just calculate the size of the cross product of two vectors to find the area of the parallelogram formed by those two vectors, which is a nice result.